Hello,
She needed
Leora,
a model for
Elisheva. Okay. Look at this picture here. This should, don't be sit down. This should be obvious, right?
We did that yesterday.
Yeah, I know. Limit register. It has to be, the relocation register is what? Is how much you add to it. But first you have to check that the address that I got is less than the limit register. That means it's within the range. Limit register is like how big of a range I have. And that I'm going to add the address to the relocation register to get the actual physical address. So that's the computation to get from logical address to physical address. Okay. We talked about fix. I think we talked about this also. But we'll go into detail of this here. Let's see. Yes, I am. Multiple partition allocation. Each process is allocated one or more partitions of memory. So here what we're going to say is we have fixed size partitions. Yeah, here I changed the slide a little bit. We have fixed size partitions, but each program can be given maybe multiple pieces. So for example, in this picture here, process 8 has several sections of memory. Yeah? You're distracting us. Just turn it off.
Can't turn it on. It doesn't. They can only do it by the.
Oh, wasn't he just here? The guy was just here.
Yeah, and he's like, oh no, it's on heat, and it was.
Press that button, that red button. No, that just turns it off.
Okay.
Yeah, turn it off.
Multiple partitions. Okay, so fixed size partitions. Degree of multi-programming is limited by the number of partitions. Right. In other words, if we take our memory and divide it up into 10 pieces of memory, then we can't have more than 10 processes running at a time, because each one's going to get minimum one section, right? So that's what I mean by the degree of multi-programming is limited by the number of partitions. But we could, of course, give one process more than one section. That's one. So that's, first of all, that's one size, fixed size partitions. Then there's also variable size partitions. Variable partition size for efficiency. Size to a given process is sized to a given process's needs. Right. In other words, the amount that the process needs, we're going to give him a variable size. So you can have fixed size or variable size. Now, in variable size, we are going to talk about, well, it also could be in fixed size, but we're going to talk about a whole. What is a whole? A block of available memory. Holes of various sizes are scattered throughout memory. So in other words, here's this gray area is a hole, is a place that's available. When a process arrives, it is allocated memory from a hole large enough to accommodate it. So particularly in variable size, if it needs a certain amount of space, we're going to look for a hole. In this case, just one hole here. Theoretically, there could be many. And we're going to look for one that fits, that we can squeeze him in. Let's say he only uses part of it. Then we're going to have a little leftover hole, which is very small. So here you see, process 9 comes and takes over some of the hole. Then process 10 comes, it takes over some of the hole, and the hole is getting smaller all along. But this picture is, you can imagine, holes could be spread around because, for example, process 5 could finish. You see process 5? It could finish. And then you're going to have a hole here and a hole here. So you're going to have, imagine in your mind, like holes spread out throughout the memory of possible places to put programs. And if it's variable size, then the holes are of varying sizes. If it's a fixed size as well, there's still kind of a variable size. Each one is of the same size, but there could be two adjacent. And if you view those two adjacent as one area, then you could have different sizes also. Because remember, we're talking about contiguous allocation. What does contiguous allocation mean? It means that the memory of the program is adjacent to each. In other words, the whole program is in one area. If it's variable size, it's in variable partition size, then it's in one partition. If it's fixed size, then it's either in one partition or in multiple. But those multiple partitions are all adjacent to each other because it's contiguous allocation. So anyway, my point was that you should visualize this, that imagine 5 is not there, imagine 5 is there, but 9 is not there. I can have holes spread out and also unavailable areas that are already taken up by processes spread out. Processes exiting frees its partition, like I just said. Adjacent free partitions can be combined. especially in the variable partition, right? In other words, if all of a sudden 2 finishes over here on the bottom, then this hole gets larger. Operating systems maintains information about allocation partitions, free partitions, or holes. In other words, we need to know at all times which memory is being used by which processes. So essentially, if you think about it, what it means is if we go back to this picture, it means that for each process, we're going to have its limit register and its relocation register. In other words, how big is it and where does it start from? Everyone follows me? Now, the relocation register is where it starts from. And how big is the limit register? That's enough. Once we have those 2 pieces of information, we know where everything is. All assuming that we're in contiguous. Imagine it, but just for imagine, we're about to get to this non-contiguous, but imagine non-contiguous. What would we have to have? It wouldn't be enough to have 1 relocation register. We'd have to have the beginning of each section, right? And if it was spread out, if it was not contiguous, if it was spread out. Remember, we're talking about these holes could be spread out. Then we'd have to keep track of where each memory section of the program is. All right, but before we get to non-contiguous, we still have this question, which is going to be with us for the next several slides, which is how to satisfy a request of n size from a list of free holes. This is called the dynamic storage allocation problem. In other words, we have to at a certain moment as the operating system is running, he's all of a sudden got to deal with allocating memory. Now, we said that there are all these holes spread out throughout the computer of memory, spread out throughout the memory. Which hole should I use? And now this is like kind of the fun part of it, which is which hole should I use? And the 3 possible things are first fit, which means the first hole that I find is, what am I going to do? I'm going to go through, imagine again that 5 is not allocated. So I'm going to go through all the memory until I find a hole that is the right size that I can use. I could, as soon as I find one that I can use that one. That would be called first fit. Yeah.
Can I ask you, does the operating system work will it have to go down in order? Will the operating system have enough insight to understand that it has to stop between processes, or it's just going to?
Well, it'll check only the ones that are free. It will check, it'll skip 9 and 10 because they're occupied. It'll have a list of which memory is available and which is not available.
Okay.
And it'll go through all the available and check. It's a loop. It has to do a for loop, right? It has to just go and check all the things until it finds one.
I don't know. I know it sounds like a bit of a silly question considering we've been doing operating systems for so long, but it's operating system. It's a program. It's not like okay.
Exactly, it's a program. It's a program that's running, that's doing stuff.
That deals with all this kind of
That
stuff.
deals with this stuff, for example. Right, we wrote a program that could be part of the operating system. We wrote that in the lab, which would be just to decide which, who to give the CPU to. Now we could write another program, which would be how to decide which memory locations to get. We could write a simulator for that.
So it's not all a hardware thing. It's all like a program based.
Well, the operating system talks to hardware, but it is software. Okay, so back to the first fit. First fit means as we're going through our for loop, the first hole that's big enough, we are going to use. It's the fastest method. Then I stop my loop quicker, right? I don't have to keep going through the loop. As soon as I find one, I'm done. It's a compromise between the next 2 kinds. Let's talk about the next 2 kinds. We'll see why it's a compromise. Well, first fit, because it could be that it's not the best fit, right? What's the best fit? The best fit would be that there's the least amount of leftover space. In other words, I have a slot that's available of 100 and I need 90, so I have 10 left over. So okay, I'm not going to use that 10, but it was better than if I had chosen, let's say, 150. If I had a slot of 150, I put 90 in there, then I'd have 60 left over. So best fit means I choose the one that leaves the remaining dead space as small as possible. That's called best fit. Allocate the smallest hole that is big enough. Must search the entire list. I have to go through everything until I have to compare them all and keep track of their sizes. Unless ordered by size, unless somehow I've ordered if I theoretically could have ordered this, if I keep track of them by their size, then maybe I could not go through them all. But the point is I have to check a lot. Produces the smallest leftover hole, right? We said that. In other words, the dead space, if I, like I said, if it was 150 and 100 and I wanted to put in 90, where would I choose? I would choose the 100 because then I'd only have 10 left over. My 90 will fit in there with 10 left over. If I choose the 150, I'll have 60 left over. That's a bigger leftover hole. Worst fit is exactly opposite. They say, no. I rather leave, this is very clever thinking here. It's the same exact thing, but I'm going to choose the worst fit. I'm going to choose the biggest leftover hole. What's the logic in that? Why would I choose dafka the 150 and not the 100 and leave a 60 section left over?
Because once it's finished, there's a lot more space left.
No. What do you mean once it's finished? What's the program? What's the process finished?
Process.
Once the process is finished, then I'm back to wherever I was. So it has no effect. Either way, I'm back to wherever I was. Once the process is finished, then the memory is released and I'm back to wherever I was. So it's not going to be the biggest possible hole. It'll be, I have a situation, I brought markers. I have a situation like this. I brought bad markers, but I brought markers. Here, this is 150, whatever, 150 megabytes of memory. And this is 100. And I have my program, my process that needs 90. So if I put it here, I'll have my process, we'll call it process one, and I'll have 60 left over. If I put him here, I'll have 10 left over. So best fit would say put him here and leave this 10 left over. Worst fit would say put him here and leave this 60 left over. This is like the unused. Now comes along process 2 and says he needs 50. Well, I'm in luck. I can put it here, right? Because I have that 60 left over. I could also, of course, if I left this 100, I could also put it here. Actually, dafka, what would I do? If I'm following the principle of worst fit, and now 50 comes along, where would I put it? In the 60 or in the 100? In the 100. So now I put it here, and I'd have.
You're able to switch them out, or you're adding to it?
I'm adding. The programs want to run at the same time in my computer. So eventually they'll finish, and then I'll have the memory. But we're talking about at any given moment, I'll have some situation of memory, and a program will come. So what's the advantage of worst fit? Best fit we kind of understand because I'm sort of like not cutting up some space that I have. But what could theoretically the advantage of worst fit? Yeah.
Because then you can actually have useful leftover storage.
Exactly. Then I'll have useful leftover storage.
And you have to keep track of all of it.
Either way, I have to keep track of it. In other words, worst fit has a certain theoretical idea behind it, which is that now I get this 10, chances are nobody will ever come around who wants that 10 because it's such a small space. But the 60 is useful, is a useful size. It's like leave enough space that I could imagine that another program would be able to use it.
Wait, so the advantage of it?
The advantage of worst fit, even though the name sounds like it's bad, worst fit is that it leaves me the largest leftover, and then that leftover piece is potentially useful for some other process that might come along. So even though on the one hand it sounds like I'm putting it in the worst place, it could be I'm putting it in the best place. So what did I write here at the bottom? First fit and best fit are better than worst fit in terms of speed and storage. So notice that if you actually run tests, turns out that worst fit is not so good. First fit and best fit are both better. In other words, if you run an operating system with all three of these and you try it with the same set of processes, it turns out in reality, worst fit comes out worse, even though it has a certain logic to it. I guess the reason why it comes out worse is because of exactly our example, where we theoretically, that's this nice 61 over, but since we're still in the process of worst fit, we're going to put it in his 50. So it didn't even help us really. If we had left, we're going to anyway put it here. We're going to anyway put it in this worst place and now have 50 left over.
Right, I guess you'd have to change the algorithm so that it works, like that you're.
Sometimes right, exactly. You'd have to do like every other time.
Right, exactly.
You could do that every other time. First time it's best fit, then worst fit. Best fit, worst fit. You could do that. You could also do something. What about this? What about random fit? Sometimes put it in the best place, sometimes put it in the worst fit, just randomly. Well, guess what? That's what first fit is. If you think about what first fit is, because I'm not checking about the size, I'm just saying the first one that fits. Which means it could be, it fits and it leaves a huge leftover, and it could be it fits and leaves a tiny leftover. I'm not even caring about it. So random fit is already.
I'm just,
So when you're going through, it's not, does it like what's the other saying that you have to constantly be like keeping track of everything? Once you put a process in, then it now sees the whatever is remaining as a new available resource, or that. is
Once you
now
put the
fully
process
considered.
in, you have like a linked list of all the, or an array of all the free memory. And you keep marked where it's this a block that starts at place 100 and ends at place 110. Another one that starts at place 300 and ends at. He has a list of all. He has like a struct of each of those things, which has the starting and ending point. And he'll go through that list of structs and he'll check. He'll do this minus that and come up with the size and then say, oh, it's too big.
So let's say it has like a few processes. So the first process, it finds a place it puts it in. Now the remaining space that process is not using of its empty space where it was put into,
Yeah.
is that now also among the potential options for process to be put into?
I don't understand. One process comes along.
Process 1 goes into 150.
Yeah.
We're doing first fit. But
Okay.
there's only, so now there's 60 remaining. Does it automatically now have 60 as a potential place to put
Yeah.
in the
Yes.
process?
Yes.
That's even the second after, or if
Yeah.
that's
As soon as
like
we assign it,
all
now
of the
60 is available. Yeah. It's not wasted because we're talking about variable fit. Remember, we talked about first fixed size and variable partition. We're really talking about variable partition here. If it's variable, then yes, now we have 60. If it's fixed size, then really what it means is our memory looks a little bit different. I didn't bring it.
there's one on the board.
Fine.
I'm a little confused, the difference between fixed size and variable.
I'll show you. I'm about to show you exactly the difference between fixed size and variable size. Probably not, but let's try it. Fixed size would be like this: 10, 10, 10, 10, 10. Imagine like that. This is location 10, 20, 30, 40, 50. And those are my six. Now a program comes along.
This is from Shira.
Thank you. A program comes along and says he wants 60. What are we, or not 60, that's too much. He wants 25. What are we gonna do?
3.
We're gonna give him this and this and also this. Now, we're gonna give him, he asked for 25, we're gonna give him 30. Because we have fixed sizes. In other words, we're not doing this variable size where anything can be any size. We're not chopping up the memory. It's like pie, if you cut a pie already with, you're at a restaurant, so you're like, when they serve slices of pie, so they cut them already in fixed sizes. But at home, you can make a piece this big or that, any size you want.
It's a waste of space.
So actually, this is great to talk about it in this context, because we're about to talk about it. We have something called, this wasted space here, because he only said he wanted 25, and I can't give him 25. I can only give him units of 10, because that's how my memory is divided. So in variable size, we didn't have that problem. But in fixed size, we do have that issue. And we're now going to have something, this filled in area is going to be called internal fragmentation. It's called internal, it's a term you have to know. Internal fragmentation, because it's internal to the allocated memory. Now, if I look in the list of memory that's been allocated, this whole section is allocated, but some of it is wasted. So that's called internal fragmentation.
It's internal to what?
It's internal to the process.
So
In
it's
other words,
wasted space.
It's wasted space, but that's internal. There's something called external fragmentation. External fragmentation is not going to happen so much here, but we're going to talk about external fragmentation more in the variable one. Do I have it on the next slide? Yeah, there you go. Next slide. External fragmentation is total memory space does exist to satisfy the request, but it's not contiguous. In other words, we'll go back to the other picture. Really,
Like it's not all in a block.
I could almost say, let's make a rule. In fixed size memory allocation, you're always going to have internal fragmentation. In variable size, you should never have internal fragmentation, but you will end up having external fragmentation. External fragmentation. Oh, I'm on the wrong side. External fragmentation is like this. Imagine you had a situation like this. Some process came and you gave him this, and some process came and you gave him this, and some process came and you gave him this, And some process came in and gave him this. And then this process finished. Yeah? So now you have you have a hole here, and you have a hole here. Now comes along a process and says he needs a space, but he needs a space that's bigger than this. So what's this? Let's describe that situation. He needs a space bigger than this section. Well, we can't give it to him because that's our biggest one. But if we would add this one to this one, theoretically we would have enough space for it. But we can't do that because he needs to get his memory in a row, in contiguous. So that's called external fragmentation, because it's fragmentation, but it's external, has not been assigned to a process. There's no process using this and no process using this. We can imagine a worse situation that somehow this, a process came along and said, oh, I want, a piece like this big. Yeah. And then we gave it to him. And then this process finished. And if this process finished. So now this is available. And now somebody comes along and says, oh, I need a space, and we give him this one. And now we have, this little sliver here available. And now, as this goes on, processes coming and going, we could end up having a situation of memory that's like all kinds of little slivers of free of memory with processes in between. And we have a lot of memory available, but we can't use it because it's all useless. It's all not big enough. So that's external fragmentation in the extreme, right? If you have a lot of external fragmentation, would mean as processes keep coming in and out, and I give them all kinds of crazy sizes, and I'm ending up with little pieces left over. And I can't use them. So what's the solution? What is a possible solution? I think I have it in the next slide. Yeah.
Non-contiguous.
Well, that's going to be the better solution. But the first solution you might think of before we're sort of in the world of contiguous. So we're in the world of contiguous. What's the solution? It says here compaction. You can guess what compaction is. What would compaction be?
Smaller, take less space.
No. You're not compression.
Shift things over.
What?
Shift everything.
Yeah, move everything. Shuffle everything down, and then make a big area in the top. And as you can move them, move all the processes in memory. Change all those registers. But what is this going to require? Copying, means copying every single byte of information here to some other location and everything. So it's going to be a whole long process. Actually, I don't know if you ever tried this on a Windows machine. I don't know if people do this, but you used to do this. You can run a system utility called defrag or defragmentation. And what it does is it goes through the memory. It does defragmentation on a disk. We're talking here about memory, but you could do this. It's the same principle in the disk. As you copy and remove files from your disk, you get little slivers of space. So a possible solution is to, move those functions, move the files and put them, compact them. Get rid of all the dead space. Just shuffle them all down. Of course, that takes a long time. That's the problem. But wait, we didn't finish something over here. So we explained internal and external fragmentation. Now it says first fit analysis reveals that given n blocks allocated, 0.5 n blocks lost to fragmentation. 1/3 may be unusable, right? So if you have allocated 100 gigabytes, there are going to be 50 gigabytes of fragment of lost bytes, of lost space, because you can't get to it because of external fragmentation. And that's called the 50% rule. In other words, 50% of what you're using, if you have 100 that you're using, there's going to be another 50 that you're wasting. That's just showing you the importance of how big this problem is. And it's going to happen either whether you do, as I said, I'm repeating myself, as I said before, if you're going to do you're going to have internal fragmentation if you do fixed size blocks. And you can have external fragmentation if you have variable size. You could also have external in fixed size, because you could have blocks of those, whatever that size is.
Wait, I thought you said you can only have internal in fixed size, but you can't have external.
Well, I'll tell you this. No, if you have, I don't know if I said only, then I was wrong. What I mean is like this: if it's all fixed size, 10 20, 30, 40, 50. Remember, I can still give somebody 3 in a row. But what if I gave somebody 2 and then somebody 2 and then somebody 1 and somebody 1 and then he finished and he finished? I could end up having sections of 10s spread out and somebody comes along and says, I want 30. And I have 30 available, but they're not connected. So even in fixed size, I could have external fragmentation. But I'll also definitely have internal fragmentation. That's for sure. I'll have internal and external. In the variable size, I'll only have external fragmentation. That's what I meant to say.
Because you can't have internal because
it's variable size. It's custom size. I made the sizes exactly according to the needs. Okay. So shuffle the memory context. Compaction is possible only if relocation is dynamic. It's right. Oh, this is an important point. Execution time address binding. In other words, remember we talked about address binding? I said it was a good conversation topic in a date.
yeah.
As a joke. So if you do execution time address binding, then you can compact, then you can move things around. But if you do, imagine doing compile time, if you create the actual address where it's supposed to be at the compile time, then you can't move it. You can't move your memory. You have a fixed address. You don't have a relocation register, right? That whole thing of the relocation and moving, of deciding where it is, you don't have logical and physical addresses. You just have one address. So compaction is only possible if you do dynamic. Of course, nowadays everything is dynamic. So there's dynamic relocation. Another solution would be to allow processes' memory to be non-contiguous and then scatter it throughout the memory. Oh, so there you go. That's what I said. What about just getting rid of this whole idea of contiguous memory? Then we don't have this fragmentation issue. We can say any memory can be any. You can have a byte over here and a byte over there.
What's the cost of that?
Oh, there's going to be costs, and that's what we're going to talk about. Consider that the backing store, in other words, a disk drive, has the same fragmentation problems. That's what I also mentioned. Right, I said the same thing. You can defragment your disk. Your disk is gonna have, it's there, it's not memory, but it's like you put a file and then you delete the file. You put a file, delete the file. You keep putting and moving and moving and putting. So eventually you're gonna have all kinds of little gaps between, because they're, remember, files are contiguous also. So there are gonna be gaps between them that you've lost the ability to use now. Okay, and now we're talking about something which is not that important, but we'll talk about it briefly. Memory management scheme. I give comments on my own on the material here. Some of it, this is important, this is not important. Memory management scheme that corresponds to the user view of memory. So, okay, so first of all, we talked about this idea of memory. Now we're going to talk about dividing up the memory by subject matter. By subject matter. In other words, instead of saying, we're going to, basically this is in the category of non-contiguous memory allocation, the question will become, how do we divide up the memory uses of the program? And this idea says, the idea of segmentation essentially says that, you know how I'm going to divide it up? I'm going to put all my functions over, or no, each function I'm going to put where in a different place. This function 1 will be here in memory. Function 2 will be here. Remember, the code itself has to be in memory. So the function that you wrote a function that does X, Y, and Z. It has to be in memory. It's machine level. You know, it's machine language. 1s and 0s need to be in memory. And I'll put each function at a different location, or maybe all the functions together. And then I'll put maybe the main program together, and I'll put, I don't know why function method, whatever. I'll put my arrays in another location. In other words, all the different parts of my program, my stack, my arrays, all the different parts of my program, each one will potentially be in a new location, in a different location. And I'll keep track of where all the different parts of my program are based on the, you know, it's kind of like, if you would keep your clothes, you know, you have a drawer for your socks, and so the socks, you have, and a drawer for your underwear, and a drawer for, and a closet for your shirts, and a closet for your skirts. You have each thing in its own place, and each person has that. So each process is going to have its, socks here. One process is going to have its socks here, another process is going to have its socks there, another one. Each one will divide up their memory needs based on the category of the memory, whether it's a function or an array or whatever. That's the idea. So here you go. Here's my logical addresses, and the idea of this, it says, notice, it says a user's view of a program, because the niceness of this way of doing it is that this is the way a user thinks about the program. He thinks about it. I've got, here are my stacks, and here are my functions. Square root is a function. Here's a function of a library function. Okay. And now here, the user views it as this: 1, 2, 3, 4. These are those sections, right? These, I don't know. Here there's 5, but whatever. We limited it down to 4. Here are those socks, skirts, shirts.
It always looks like this on the left, the user space? Or
It's
does
just,
this
just an example. It's an example. In other words, you have these functions, these different sections. You have a main program. Well, every program is going to have a main program. It may not have square root, but it'll have different functions and different arrays. And here you go. This array, this section is in 1. This is in 2 is over here. 3 is over here. 4. So this is non-contiguous memory allocation. And I'm going to have to keep like a relocation register for each type of, or each particular function that I'm talking about. Yeah? Okay. So logical address consists of a 2 tuple, segment number and offset. In other words, notice that these are segments. Segment, 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 and they have a number, 1, 2, 3. So I say function, my function is in segment 1 at offset 100. That's where the function starts. That's what my program is going to look like. But and it actually has to go find it. It's going to have to map to this location and go 100 off from the beginning, from wherever 1 started. So we're going to have a segment number and an offset. Segment table. We're going to have a segment table. It maps a 2-dimensional physical address. Each table has a base and a limit. So for each segment, I'm going to have a base and a limit, where it starts and where it ends, where it starts and where it ends, where this 2 starts here and ends here.
Can I ask a question?
Yeah.
So the offset is always starting from like the top of the memory, like, or is it starting from the
Yes.
previous segment?
No. Oh, no, the offset is internal to the segment. 0 would be the beginning.
Okay, so like in the picture we had above, like for segment 2, you would do, the offset would be like all the way from the top of 1 all the way down to 2, or would it be from 4 to 2?
Everybody's, the first line of each segment will be offset 0. We offset 0. Okay.
So then what's going in the offset field? And I thought the offset's telling you where the memory it is.
Yeah. So, okay, I'm sorry, I misstated. You're right. The segment table, the base is the starting physical address where the segment resides. In other words, we're just talking about where does 4 start? Where does 2 start? Yes, I'm sorry, I said that wrong. 2 starts here, let's say, at line 100, and 4 starts at, let's say, line 20 in the memory, in the physical memory. So I'm going to have to keep track of where each segment is. That's all.
Is that what goes in the offset? Like where it
That's
starts?
this base and limit.
Then what's the offset?
The offset is, in other words, there's 2 things going on. First of all, the operating system has to keep track of where all the segments are. Secondly, when over here in my code, what's address am I going to say here? I'm not going to say address 100 and then he just adds. I'm going to say I'm going to say base. I'm going to say segment number and offset. I'm going to say go jump. If I have a jump command, I'm going to say jump to this segment, to segment number 4, offset 12. So he's going to jump from here to here.
Well, what's offset 12? Like, well, what's that value? Where's that value coming from? Like, how do you how do you visualize what the offset is?
The offset is where in the segment I want to jump to. Where,
It's like if you're.
if I have, let's say, several functions in this section, and I want to jump to the third one, I'm going to jump to whatever offset that has to be.
Oh, okay, so it's viewing, like, so there's actual physical place where each segment is in memory, but then within each internally, each sort of starts at 0, but then you wanna jump to a specific spot, that's the offset?
Yeah, yes. Each segment conceptually starts at 0. So as when I want to jump to someplace in 4, I got to tell it, first of all, that I'm going to 4. And second of all, how much from the beginning of 4. Now the operating system is going to have to keep track of this second thing, this base and limit, where 4 actually is in physical memory. Segment table base register points to the segment table's location in memory. So that means the operating system is going to keep track of an STBR, of a segment table base register, where each segment is. As the program, in other words, this first bullet, this first square bullet is what the program is keeping track of. The program has a segment number and its offset. The operating system has to keep track of the other bullets here, the segment table base and the length. Indicates the number of segments used by a program. Segment number S is legal if it's less than STLR. This is just how many segments there are. In other words, if he tries to go to segment 5, it won't work. He'll be caught. Yeah, I sort of want to get through this really quickly. Protection. With each entry in a segment table, associate a valid bit 0. Valid bit equals 0 is an illegal segment.
What does that mean?
Well, I'm not exactly sure why we need to have it, but I know what a validation bit. A valid bit means that in addition to keeping track of where the segment is, we're going to label it as either 1 or 0. 1 meaning that it's permitted to go, it's valid, and 0 meaning that it's invalid. Maybe it means that it's not in memory at the moment. In other words, this segment could be, this 4 here, I'll explain to you. This 4 here doesn't have to be in memory. It could be on the disk. It could be that I want to get it and I go and I say, oh, it says go there, but it tells me where it's supposed to be, but it's not there. But the valid bit is set to 0, means it's not actually there. And then I'm going to have to go to the disk, and then I have to tell the operating system is going to have to go to the disk and bring it back from the disk and put it into memory. But really, that we're going to talk about more about that later. That's what a valid bit is.
Was you telling you whether that you're calling it is or isn't in memory?
What?
It's telling you whether something is or isn't in memory.
Yes, the validation bit. Also, there's read, write, execute privileges you can have. For example, there may be, let's say, for example, here he wrote square root. What is square root? SQRT. That's a library function. I can run that program, but I can't alter the lines of that code. I'm not allowed to, it's not my, there might be somebody else. In fact, there might be something called shared memory, right? I don't know if we talked about that. Did we talk about that, shared memory? I don't know.
In the lab, we did.
No, I don't mean that shared memory. I mean shared libraries. We talked about shared libraries.
So.
Yeah, we talked about shared libraries. So SQRT is a library function. So it might actually be that if I have 2 processes and SQRT is used by both of them, then the segment that has SQRT is actually associated with both processes.
Oh, yeah, we did see that.
Yeah, is associated with both processes, and they both are read. So I don't have to load into memory SQRT twice. I can just have a segment for SQRT, and anybody who wants to use it has it added to their table of legal locations, of legal memory addresses. But it'll be marked as not writable. I can't write to it because it's not really mine. I can't write to that memory. So that's what he's just saying here about I can also keep read, write, and execute privileges. Code sharing occurs at segment level. Right, that's exactly what I just explained here. Protection bits associated with segments. In other words, we can protect the segments and we can have code sharing. Since segments vary in length, memory allocation is dynamic, storage allocation problem. Since segments are, we're going to back to have our problem again. of finding the right place to put every segment, right? Even if, the point is like this, even if we, how should I say? Well, the whole point was to have variable sizes. But actually what we did is we just chopped our program up into smaller sizes. We didn't actually make it infinitely choppable. We just said, we're gonna have segments and now it's smaller, and so we'll find better places, but we still have the same issue. We're still gonna have to put each segment in some location. All those, right? In other words, we're gonna still have to find a place to put it. A segmentation example is shown on the following diagram. Okay, so.
Wait, just to go back a second. So just, so like how we learn in all of our, with programming and everything, if it's 0, then it's illegal. It's not, it's false.
0 is false, yeah.
Okay.
All right, let's look at this example here, and then we'll go to paging. Here is an address. The CPU, notice when it says CPU and an arrow, means CPU produces an address. And the CPU produces an address. What kind of address is that? That's a logical address, right? We're gonna have to convert that address into what? A physical address. Hope everybody should answer that question. Physical address. We're going from logical to physical.
Is that what that arrow is?
That's what this little diagram is. Wait, let's go slowly. So what we're doing is we're going to take a physical address here. Remember we said it's composed of two parts, a segment number and an offset. So here is the S number, is the segment number, and the offset. So here we're going to go to our segment table. Our segment number, the address is just a number. Jump to address 00152, whatever, 110011, whatever it is, ones and zeros. But we're going to take the first half of the address and we're going to view it as a number, because the first half could be 001, so, or 0011. So if it's 0011, the first half, then that's 11 is what? 3. So it's segment 3. So we're saying the meaning of that address is go to segment 3. But I'm going to go to segment 3. And
Is D the offset, or the offset is in S also?
you see what he did here? Look, if S is 3, wait a second. Imagine this is a 8-bit address. So it's 0011, and then over here is, let's say, 1111. I don't know, some other number. The whole address is 8 bits, but I'm just gonna look at the first 4 bits. 0011, I get 3. So what I'm gonna do is I'm gonna go over to this segment table and I'm gonna move down this number, 3. So if I would be 0 here, if we 0000, then I would stay at the first row. But I'm gonna go to the 3rd row, and now I'm in the row 3. And that row 3, I'm gonna have data. I'm gonna have ones and zeros. Now, what is that number? I'm gonna have, let's say it's 2 bits here and 2 bits here. Remember I had 4 bits? Let's say the limit is 2 bits. So the limit is gonna tell me the size. And that is, how big can it be?
But then it would be 00.
Wait a second. Oh no, it's gonna be 4 bits here. It's gonna be 4 bits. Let's say this is 1111, and let's say the limit here is 1111. So then, or let's say the limit has to be more bits actually than this. So this will be 4 bits. The point is, this 4 bits is gonna go into here, and then it's gonna get from this table maybe more than 4 bits, maybe 8 bits, and then it's gonna get a number over here. And as long as that number, that kilo offset is, that's really like an offset, that D. As long as that offset is less than the limit number that I got here, then everything is good. Then I'm below the limit, I'm within my range. Then I'm gonna take the other half of the number on that row, which is gonna be basically my relocation register. That base is where to find the segment, right? Are you with me? The base is where to find the segment. So now I'm gonna add that to this D. In other words, I'm gonna put it on the left side of this D. I don't know if it's really an add. It really should be on the.
Is the D the
It
offset
could be,
or
all
it's
right,
not the
it could be just a
offset?
plain add, doesn't really matter. But what?
Is the D the offset or that's in the S?
D is essentially the offset.
And what are we using to find the segment? The base? Or that's also part of D.
You see, D went in here and made sure that the offset was valid. Now I'm going to push that offset over here, but I'm going to add it to this base register, which is going to be essentially my relocation register and tell me where to find the segment that I was looking for. I was looking for segment 3, right? Segment 3, its base is here, because its starting point is whatever is values in this, on the second half of this row on this table. So I'm essentially replacing this gray area here with whatever base is. Whatever S was before, I'm going to replace with base. And now I'm going to move, in other words, if this was 0, 0, 1, 1, so it's 3. But the base could be 7. So it's going to be, what's 7? 1, 1, 0, 1, 1, 1. So it'll be, instead of 0, 0, 1, 1, it'll be 0, 1, 1, 1. And now I'm going to put that at the left side, and I'm going to carry on this D, and I'm going to jump to location 7 in memory, you know, or it's actually going to be larger. It's not going to be the exact same size of base. It's going to be larger. I'm going to go to some place in memory based on this base. Then I'm going to add to it the offset, and I'm going to get to the actual memory where I want to be at. In other words, you understand what I'm saying?
D is only invalid if it's 0.
Oh, I see. I keep writing on this, right? In other words, let's forget about zeros and ones. Let's take a number. Let's say this is 3. So 3 tells me go 0, 1, 2, 3. So it takes me to that row. Now I get a number over here, base. And let's say the base is 10,000. So, and now let's say this number is 50. Okay? So that's the address. The CPU said jump. There was a jump command, right? And the jump was jump to this number, 350. I mean, it's really ones and zeros, so it's one long address. But whatever, this jump to this address. We're going to take that address and chop it in some way. It doesn't have to be down the middle, but we're going to chop it in some way and take part of it and call that S, part of it and call that D. And that S we're going to use to tell us to go how far down in our segment table. And then we found the right row. And now it tells us at that location, now it could be over here, there's 20,000, right? And it could be over here at 4, there's 15,000, I don't know. Any numbers are possible. But I got 3, so it told me take the 10,000. Now I take the 10,000 and I put it here. And I check my D. Is my D less than whatever the limit is? Let's say the limit here is 100. The value in that row is 100 over here and 10,000 over here. So 100 comes over here. Oh, wait. 100 comes over here. And I check, is 50 less than 100? Yes, it is. So carry on. Now the 50 goes over here. And I combine them and I get 10,000 and 50. And this is my memory. Now my memory is 0, you know, dot, 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 5,000, dot, 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 10,000, dot, 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 15,000, up till, you know, 2 gigabytes. That's all my memory. So I now got this jump command that said jump to 350 is now going to actually go to this location of memory. It's going to go somewhere over here and do whatever is written there. That's the idea. But I need to maintain a segment table for each process. The operating system needs to maintain this for each process to know what to do with this address and how to convert it to the right segment. Yeah.
What did your S do?
My S found me the right segment. He said, I want to go to segment 3. He said, jump to segment 3, and inside of segment 3, go to line 50. That's why I call that the offset. But this is the segment number. That's why it's S. And that took me to the segment table, where I have a list of all the segments and where their bases are.
Wait, but you said
If we're in segment 3, but then with that block where the limit and base are, is that a list of all the segments? That's a list of a specific segment.
No, that segment table is a list of all the segments for that process.
So then where's
For that
50
process, very important point.
So then where's 50 going? Like where's 50?
Oh,
taking?
50 is, well, because it told me, this is a particular line, 10,000 is the base, right? And the limit is 100. So that means the segment 3 is actually here.
Did you randomly decide the base number? Because you
Yeah.
put 2 at 2, 20,000 and 4 at 15,000.
Yeah, exactly. My point is that they don't have to be in order.
Okay.
That was why I did it like that. 20, 10, 15. There's no order. They're just wherever they happen to be. But to look at the limit is only 10, is only 100. So actually this is 10,000 and this is the segment, 10,100. Yeah? That's what that means. Its base is 10,000, its limit is 100. 10,000 until 10,100. Now he wanted to go to offset 50. So he's going to be somewhere right in the middle here. That's the row that he wants. That's the 50. What the offset is within the segment. This is segment number 3. Segment number 2 is down here. Segment number 4 is whatever. They're in different locations.
And it will only take up the amount of space that limit is?
Exactly. It'll only take up, because we're dealing with variable size, yeah. I mean, it doesn't have to be. I mean, yes. There's no, it could be, how should I say? The limit is how far it can go in that segment. If I have fixed sizes, then it just means the limit will always be a multiple of something. It'll be, thousands or whatever, it'll be some multiple. But if it's variable size, then the limit will be anything.
It's the most it could take up.
It's the most it can take up.
So how does it know how much to take up?
No, when I compiled my program, I created segments. The compiler created segments and said, this segment needs 100, this segment needs 200, this segment needs 300. So then if it was variable size, then I'll create exactly those size segments over here. The operating system will grant it exactly those segments. If it is fixed size, then it'll grant it maybe more than it asked for.
So why does it need the limit if it already has the size?
Because I have to know, because maybe maybe I'll try to jump to segment 3, location 10,000. I want the operating. I want the operating system to prevent me from doing that.
Okay.
I just want to. I want to keep within my bounds. All right. Let's. That's it. Now we're going to do something that looks almost exactly the same, but this is actually the more important. Remember I said this was not so important? So now is the more important thing. How much time do we have? We have 20 minutes, yeah? Okay. So that's good. So paging. Paging is a major concept. It's based, I mean, I think the reason why we teach segments first, it's a very weird thing. How did it stay there?
It's a magnet.
There's metal here? Not sure if it's a magnet. It does kind of feel like a magnet, yeah. Okay. What was I saying? Yeah. So why did we teach this segments? Because we don't really do segments, actually. But it teaches you this idea. It teaches you one important idea, which is that the logical address that you generated can be viewed as a series of bits and can be chopped up anywhere I please and can be used to map. There's the physical address, the logical address can contain within it the information that allows me to map it then to the table, well, to that mapping table. And then, in other words, this idea we're going to use again. That we take some of the address and use it to get to here, and then we replace, and then this S gets replaced by whatever in the table. That idea we're going to use in paging, but paging is a little bit different than segments.
Paging with page tables?
Paging is with page
I
tables.
think Avi did some of that with us last semester.
In what?
He based it off the textbook slides, not off like the course
Uh-huh.
slides, so.
Yeah, there's a little bit of overlap between these courses.
Yeah, so he did like page tables, like virtual memory, like at the end of the course.
Yeah, so we're gonna get that. So there you go. We're gonna do that again. For anybody who remembers, that's great. Physical address. So let's talk about paging. And like I said, it's a big topic, an important topic. Physical address space of a process can be non-contiguous. So we just saw that actually in the segments also. Process, but in paging also it's non-contiguous. A process is allocated physical memory whenever the latter is available. Okay, so we can give it memory, I guess on the fly as it's running. We are going to try to avoid external fragmentation. What's external fragmentation?
Unused spaces, concept.
Right. We are going to completely eliminate external fragmentation, actually. But we're not, notice it does not say we're going to avoid internal fragmentation. So what is the page? We actually kind of talked about it already before. When I said that you could have fixed size allocation, it basically pages is like this. It's saying like this. We're going to have fixed size, but non-contiguous. That's what we're saying. We're going to have fixed size blocks of memory. We're going to call them pages, and they don't have to be contiguous. Up till now, we said we're going to have contiguous, but even if we had fixed sizes, we would say I have to find 3 in a row. If I want to give somebody 30 and my size is 10, I got to find 3 in a row. And if I can't find 3 in a row, it won't work. Now we're going to say, based on this idea of segments, we're kind of similar to the idea of segments. We're going to say, no, I can give you any 3 blocks of 10 to get your 30. As long as I have 3 blocks of 10 anywhere in memory, and you need 30, I'll give you 3 blocks that are not connected. Okay, so that's the basic idea. Avoids the problem of varying size memory chunks, right? Every memory chunk is the same size. Let's say 10, whatever, But we're going to call it actually a block size, even though we could really call it a page size. But we're going to call it a block size, yeah.
Would you have to be select, because let's just say you have 25, every block's 10 cells of 10, and you have 25 that you want to place in.
Yeah.
Would you pick could you go like 7, 7?
No. We have fixed size blocks. Yeah. We have a fixed block size. So that means that, let's say they're all 10. So I'm going to have to give you 30, even though you only wanted 25. So I'm going to have what we call internal fragmentation. But I'm not going to have, that's why it doesn't say avoids internal fragmentation. It says avoids external fragmentation. Because even if I have a 10 somewhere down at the bottom, I'm going to be able to use it. It's not, and I'll never have a 5 somewhere down at the bottom. Every block will be the same size. So there's no blocks that are too small. I don't have to worry about best fit, worst fit, right? Best fit, worst fit doesn't make sense here because I don't care where the blocks are. They could be all scattered throughout memory. There's no need for them to be adjacent. So divide physical memory into fixed size blocks called frames. So we're going to have actually these 3, it gets very confusing. We're going to have 3 terms that are all the same, pretty much. Frame, page, and block. But we will use them in different ways. They're all going to be the same. If the frame size is let's say 100, then that means the pages are 100 and the blocks are 100. But we'll specify what frames are and what pages are. So look, divide the physical memory into fixed size blocks called frames. So if we use the word frame, we're talking about physical memory. Notice the next bullet. Divide logical memory into blocks of same size called pages. So when we're talking about the logical address, we call it a page. When we're talking about the actual place in memory, we're calling it a frame. But either way, they're the same size. They're the block size. So we could call it all the blocks. But it's nice to have the term. Everything is a block, but we could term frame for physical and page for logical. So size is always a power of 2 between 512 and 16 megabytes. So we're going to say, let's talk about it being 512 just for convenience. Think of your pages as always being 512. That's a small size. Notice that it's not going to be more than 16 megabytes, which is not that big. But back then, actually at a certain time it was considered quite big. Keep track of all free frames. The operating system is going to have a job of keeping track of all the free frames and all the occupied frames to know who we can assign to what and who is assigned to what. He has to know, oh, this process has got frame number 1, frame number 2, frame number 10,000. If you have, for example, here's a good question. If you have 4 gigabytes of memory and your frame size, here's math. 4 gigabytes of memory, Frame size is 16 megabytes. 4 gigabytes memory. Block size equals 16 megabytes. How many blocks? Right? You see the question? This is a very basic question, but we should address it.
They're asking how many blocks, they're also asking how many frames.
What's beta S?
Yes. I'm talking about frames because I'm talking about physical memory. We have 16 megabytes physical memory. Physical memory. BS is block size. Block size is 6. So how many, when I say how many blocks, fine, I can change that to how many frames. So what do you have to do? What do I have to do to get the answer? Divide, right? Everyone sees that? Divide. The block size is 16 megabytes. Let's convert this into megabytes. Well, 4 gigabytes is,
10 to the 9.
yeah, it's actually going to be, we could get an approximate answer off the cuff by just saying this is 4,000 megabytes. This is 4,000 megabytes divided by 16 megabytes. And we get 4,000 divided by 16 is some number. I don't know. 250? I don't know. Yeah? 250. After all these years of doing math, I can sometimes do things in my head. Okay. But that's wrong, right? That's wrong. Everyone knows why that's wrong?
Because it's not.
Because 4 gigabytes is not 4,000 megabytes. It's 4,000. It's 4 times 1024 megabytes. That's what it is, right? So it would actually be
4096.
what? 4096 divided by 16, which will be a little bit more than 250. Get that in my head.
Is it 256?
9.
Yeah, 256.
256. So 256. Ah!
No, it's,
And then we got a nice number, 256. That number looks nice, right? Because what is that? That's a multiple of, that's a power of 2. The power of 2. Well, actually, we could do this whole thing in powers of 2. Let's do it again in powers of 2. Because that's really that's the right way to do it. So 4 gigabytes is actually what? 4 gigabytes is actually
2 to the 9.
is 2 to the square times a gigabyte, which is exactly 2 to the 9th. So it's 2 to the 11th. And 16 megabytes, a megabyte is 1,000,000 bytes, right? So that's 2 to the 6th. So this is 2 to the what? 2 to the 4th times 2 to the, what did I say? 6th. So that's,
2 to the 10.
wait, we're doing something wrong here. 2 to the 4th? Wait,
Right.
I did something wrong here. Maybe not. Oh, that should equal 2 to the 10th. That can't be right. I must have made a mistake here. Because now I wanted to say divide this by this. And you should get just 2. What did I do wrong? Something wrong.
The final answer was 256, right?
Yeah.
You're supposed to get 2? What is 256? That's megabytes or gigabytes?
No, that's the number of blocks.
Oh.
Why is this wrong?
Well, you're supposed to get 2?
No, this would give you an answer of 2.
Why are we doing 16 times by 2 to the power of 6? Why are we doing 2 to the power of whatever 2 to the power of 6? Why wasn't it just 2 to the power of
'Cause a
2 to the
megabyte
power of 9?
Is a megabyte is 2 to the power of 6.
And then we have 16 of those.
And we have 16 of those.
But that's already, you have 16. Then there's something, you've left out some sort of conversion because you times by, the one is a megabyte and the one you convert to megabyte, why are you converting the megabyte to something else?
No, the gigabyte.
I'm trying to get everything into twos. Forget it, I'm trying to convert everything into 2 to the power of something.
It should be 2 to the 8 on the end.
What? It should be 2 to the, yeah, I must have done, something is terribly wrong. I don't know why.
Or why not just do like this and then at the end convert it?
I'll have to think about that. I don't know why. Maybe, Zahava, you work on that. What did I do wrong? I don't know. But that's the basic, that's very strange. I have to think about that. But the first answer we got is right. It's 256 blocks, okay? But that was with a very large block size. What if we had a block size of 512? 512 what? What does that mean, 512? Bytes. Very much smaller than, that's 2 to the what? 2 to the 9th, I guess.
Oh, I know why, 1 gigabyte is 2, no, wait.
Yeah, wait a
This
second.
is 2 to the 30, and 1 megabyte is 2 to the 20.
Yeah, I was something wrong. There you go. Thank you. Yeah, thank you. Okay. Yeah, I said that totally wrong. I was thinking 6 to the 9 is wrong. 4 gigabytes, thank you, is equal to 2, okay, is 2 to the squared times a gigabyte, which is 2 to the
To the 30th.
to the 30th. Okay, because let's write that down. Gigabytes is 2 to the 30th, megabytes is 2 to the 10th, and
No,
kilobytes,
isn't megabyte 2 to the 20th?
oh, sorry, to the 20th,
Well, we
2 to
get
the
this
10th.
conversion.
There you go. This is what you have to remember.
I took this off my cheat sheet from last semester.
Yeah, exactly.
Gigabytes is 2 to the 30. Remember, it's by tens. It always goes down by tens. I was thinking it was 3 because I'm thinking decimal. I was thinking decimal because a million is like 3 more zeros. Yeah, that was totally stupid. Okay, right? A gigabyte is 2 to the 30th. A megabyte is 2 to the 20th. A kilobyte is 2 to the 10th, and a byte is what? 2 to the 0. But that's, you don't have to remember that. Okay, so 4 gigabytes is 2 times 2 to the 30th, and that equals 2 to the 32nd. And 16 megabytes is equal to 2 to the 4th times 2 to the 20th is equal to 2 to the 24th.
And that's 2.
And now we divide these two and we just subtract, and 32 minus 24 is 8. So 2 to the 8. And that's our answer. That's how many bytes. But let's change it. Let's say that we only had 512 bytes.
For what?
Sorry, the 512 bytes is the page, is the block size or the frame size. 512 is what? 2 to the 9th. So that would be divided by 2 to the 9th, and we'll get 2 to the 23rd. 2 to the 23rd, which is approximately, well, 2 to the 20th is already a million, right? A million. So it's 8 million, right? Something like that. I'm just pointing out, if we had this small page size of 512, we're going to have, just to have that ballpark figure in your head of, we're going to have 8 million pages, right? So we're not going to have fragmentation, but we're going to keep track of a lot of pages. We're going to have a page table. How many rows? If we want to keep track, if the operating system is going to keep track of every page and who's using it, how many rows will be in that page table, and whether it's free or not, right? I got to keep track of whether it's free or not, that page. And if they're 512 and I have 4 gigabytes, how many rows will be in my page table? We just said it'll be 2 to the 20th rows, 8 million rows. And that page table has to be in memory also. So there's no such thing as a free lunch. You understand? We're going to have to store in memory. We're going to have to waste a lot of memory to keep track of all of our pages. So back to the slide. Divide logical memory into blocks of the same size called pages. Keep track of all free frames, right? We're going to have 8 million rows in our in our page. To run a program of size n pages, need to find n free frames. Right. If your program size is n pages, remember pages means whatever size your page is, then I'm going to have to find free frames, obviously. Set up something called a page table to translate logical physical addresses. Right? We have to keep track of where your pages are. Backing store likewise split into pages. We can also chop up the disk into pages. And then we're going to have what I would call virtual memory, where some of the memory could actually be on disk, and we can bring it in when we need it. We are still going to have internal fragmentation, right? Why internal fragmentation? Because remember, this avoids external fragmentation, but we talked about that. It's going to still have internal fragmentation because it could be I need only 1 byte of memory and I need to have a whole page, right? If I could be I need 5, let's say my page table, my frame size is 512 bytes and I need 514 bytes. So I'm going to have 2 pages, one of 512, another of 2, which will have a lot of blank space in it, right? Understand? That's called internal fragmentation.
Like 2 minutes.
Yeah. Well, let's just do this quickly and we'll come back to it. Address generated by CPU is divided into a page number and an offset number. So just the same thing. Every address that the CPU generates is actually going to be divided into 2 halves, a page number and a page offset. But it's going to look like an address. You can say jump to 111.000.111, but the first set of ones and zeros is the page number, and the second set is the offset within the page. Combined with the base, so here's the diagram. It's pretty much the same as what we saw before. The CPU generates this address. Jump to location, blah, blah, blah. So we're going to take the first part of it, and we're going to say that actually means in the page table, you see, actually, there's a page table for each process. For each process. And if I say jump to some location, let's say, again, 50, let's say 5, and let's say 50. So 5 is going to be 0, 1, 2, 3, 4, 5. It's going to say, go to this row in my page table. And now, this is kind of the way I explain the segments exactly like this. Take that 50 and put it over here, keep it over here. But now whatever is here, take that. And that's going to be which physical page to go to. So it's going to be, for example, 10. So now I'm going to put 10 over here. And then this is going to go to, this is going to be page, well, these are very big pages, but let's say, why does it say F there?
That was from the page table.
That's the frame size?
No, I think that's the actual.
Oh, F, right, 10. So, exactly. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say. Here is, these are each frames. I'm ignoring the way he drew the lines. 7, 8, 9, 10. So this is going to say inside of frame 10, now go to line 50.
That is, oh, so in.
Because this size is, let's say, 512 bytes. That's the smallest size it's going to be. So line 50 means go to memory's location. Well, it can't be 50, it has to be multiple of 4. So I don't know, what's multiple of 4? 48. Is that multiple of 4?
It's not a power of 2, it's have to be a power of 2.
Oh, it has to be power of 2, yeah. Power of 2.
Like 16.
No, not a power of 2, it has to be a multiple of 4. Yeah, 48. 40, yeah, 48. 48. Or let's take it more simple. 4. So it'll be not the first, it'll be 4 will be, right, the first one is 0, 1, 2, 3, 4, and then 1, 2, 3, and then 4, 5, 6, in other words, it's 4 bytes here, starting there. So again, the P here is telling me, go to the page table. The page table is telling me where actually it is. Now, if I want to go instead of 5, I want to go to 450, then I'm going to go over here, and it's going to have, let's say, number, it could be 20 over here. And then my address will now be 50, and this will be 20. And now I'm going to go to page way down here, page 20, and then address 50 inside there. So that's what allows me to have my memory not be contiguous. Right? You see how it's not contiguous? I have from my logical perspective, I went from 4 to 5 or 5 to 4. They were just nearby addresses. But actually there's a whole gap. And inside of here might be a memory for some other process that I have that's not mine. But from my perspective, from the program, from the CPU, he's just saying go to another address, all in order, all next to each other. But this is causing me to jump to different locations in memory and giving me a ability to be non-contiguous. So we'll stop here. You're in the exam, you're going to be given questions like, if the address was generated was, 1101111, and the, page size was 56 bytes, which page am I going to?
Are we getting a cheat sheet on this? Can we make a cheat sheet like we did for computer architecture?
Possibly. I don't know, but what would you put on a cheat sheet? I don't know.
Well,
No, just
conversions.
information.
Oh, different conversions, yeah, that would make it easier. I'll think about it. But again, wait, let's just think about that for a second. 56, if it's 512 bytes, how many offsets are there inside it? How many offsets there? Well, there's 512 offsets, which is what? 2 to the 9th, which is how many bits? 9 bits. So if my address is, let's say, 32 bits, I know that the last 9 from 0 to 8 is the offset. And therefore, that's the D. And therefore, this is the P. And therefore, I can tell you how many pages must I have. I must have 2, if this is 32, 2 to the 24th pages. So how many bits are the P? The P is 24 bits. See what I mean? You can always start with the offset. If the offset, if you know the size of the page, then you know the size of the offset, because I've got to get to every single bit, every single byte inside the page. And then what's ever left is the page number. And that for however many numbers of pages I could possibly have tells me how many pages I have. I confused you.
Wait, what's the number?
We'll do it again, but you could try an example yourself if you want, but yeah, we'll do it again.
The number 32 is how many bytes are in the address, or that's 512?
512 is the size of the page or the frame,
Okay, that's not good.
and 32 is the size of the address.
Okay.
With those 2 pieces of information, I can figure out how many pages I must have.
Can we do another example?
What?
Can we do another example from?
Yeah, we'll do. Not today, but yeah, we'll do. Yeah, next. We'll start here again. Like I said, this is a nice mathematical. Although you did a little bit of this in Avi, no?
Yeah, a little bit, yeah.
Sometimes